So here's a video for the end of the 4.2 packet where we're just going to talk about blocking. So we've talked about experimental design and this little way with arrows to sketch it out. So now we're going to talk about blocking. Now remember, the key in an experiment is that we have a treatment we apply and then a control group where we don't apply that treatment, and preferably apply some sort of placebo so that they don't know if they're getting the treatment or not, so that that's not a possible lurking variable. So again, if we have taken an SRS, a simple random sample from a population, then we can apply the results that we get from an experiment or a study to that population. Now, if we have random assignment within an experiment, so if when I have my group, I flip a coin or use table D or use a table of random digits or my calculator to assign randomly to two different groups, then that random assignment should hopefully make roughly two comparable groups so that I can account for lurking variables there. And that allows, for that reason, it allows me to determine cause and effect, meaning is a change in my explanatory variable causing a change in my response variable. So now, if we think we have another lurking variable that we haven't accounted for, then what we do is we block. And we do that before a random assignment. So this would occur after our SRS, if we have one. And if we have another characteristic. So it's similar to stratified random sampling in the sense that there's some characteristic that we think is affecting the outcome. Now the difference is it's not a study, it's an experiment. And so we have our group, and then before we randomly assign to groups, we'd split the two groups up based on that characteristic. So again, if we thought gender was affecting the outcome, then we would get our group and split our group up into females and males, and then within the male group, randomly assign half to one treatment and half to the other. Within the female group, randomly assign half to one treatment and half to other. Then we compare the female treatment group to the female control group, and the male control group, the male treatment group to the male control group. So that's the idea of blocking. Now let's look at this with experimental units in this example here about chocolate chip cookies. So these are experimental units because it's not people. And we have a baker here that would like to compare two different types of chocolate chip cookie recipes. Let's call them A and B, recipe A and recipe B. So she's got 10 volunteer taste testers. So again, they're volunteers, so we wouldn't be able to apply this to a broader population. Whatever results we get, we could only apply to those volunteers. They're going to rate each cookie on a scale of 1 from very bad to 5 very good. She's going to make 10 of each cookie for a total of 20. So we have 10 of recipe A, 10 of recipe B. Each cookie tray only holds 10 cookies, so she'll use 2 trays to bake them at the same time in the same oven. One sheet on the lower rack and one sheet on the upper rack. Now we know the oven is warmer on top, so because they bake differently depending on which rack they're on, we're going to use the 10 locations on the lower rack cookie sheet as one block and the 10 rack on the upper as the other block. On each of the sheets, Annie will randomly place 5 type of each cookie. So because the place in the oven might affect them, how fast they cook because of the temperature difference, we're going to randomly put 5 of each on each cookie sheet. That way we're accounting for the fact that rack location might affect the tastiness of these cookies. So now what I want you to do, here we have the locations in the oven are the experimental units and the recipes are the treatments here. So what I want you to do is draw a diagram in your packet, starting with the 20 locations in the oven and ending each block with comparing the tastiness of the cookies. So you'd be filling in these blanks. Pause right now and give that a try. So here we have our 20 locations in the oven. We break up 10 for the top rack, 10 for the bottom rack. We have random assignment where 5 of type A go on the bottom rack somewhere, 5 of type B go on the bottom rack somewhere. Separately, we have the random assignment 5 type A and 5 type B. Now notice we're only comparing type A and type B within the top rack. So now at the end, when somebody tries them, they'd be trying just top rack type A and top rack type B. Then they can just really pinpoint that the recipe, not the location in the oven, is what they liked. You know, some people like a softer cookie, some people like it to be more crunchy. So that accounts for that. And then somebody tasting type A and type B would be just from the bottom rack. Alright, so that's blocking. Here we thought the location in the oven could be an issue, so we separated into top rack and bottom rack and then randomly assigned. So now try this example about a cell phone company trying two different keyboard designs, we'll call them A and B, for its new line of cell phones. They'd like to conduct an experiment using subjects who are frequent texters and who are not frequent texters. So the subjects will be asked to text several different messages in 5 minutes. The response variable will be the number of correctly typed words. Now, with this in mind, why might it be better to have a block design than just have random assignment within this group? Pause right now, think on that. Well, a randomized block design would help account for experience with texting. Somebody who texts more often is likely to be able to text more correctly spelled words. So experience with texting is a lurking variable that may confound the study. If we have a lurking variable that we can identify that may confound our study, then we would block for it. Try outlining a randomized design for this type of a study. Pause right now and complete B. So we were told we have 100 experienced texters and 200 novices. Prior to randomly assigning them to one of the keyboard designs, we break them up based on their experience with texting. 100 experienced texters in this group, in this block, and 200 down here. Then we randomly assign, splitting half of them to type A, half of them to type B. So this would, if we took an SRS of all texters, then we could apply our results to the population of all people who text. We randomly assign, so now we can determine cause and effect, at least for this group. If we took the SRS, then we could apply that to a bigger group. We randomly assign to type A and type B, and we can compare amongst experienced texters and amongst novices to see if which design is more effective. So that's our whole video on block design. Now I want you to keep in mind two of the key ideas: that a simple random sample is needed to apply results to the population from which we took that sample. If we don't have a simple random sample, if it's volunteers, then any results we get can only be applied to those volunteers. And we need to have a treatment in order to determine cause and effect. We need to have a treatment and preferably a placebo group. So everything we're talking about is trying to get bias out of collecting our data. So removing bias by accounting for lurking variables, including ways like block design, including having a placebo so people don't know if they got the treatment or not. Always to try to be objective and just seek the truth in whatever experiment or study we're conducting. It'd be a great idea. Look over Lesson 1 and Lesson 2. Complete that quiz bank for Lesson 2 now for our quiz on Monday.